Okay, so we have started discussion on this buffer cache management, and we have said that the data is stored on the direct access storage device or hard disk in the form of blocks. So whenever you have to access any data from the hard disk, the data has to be accessed in the form of blocks. I cannot access a single byte or a single character from the hard disk. So the entire block has to be read, and to reduce the frequency of disk access, what is done is the block of data is put into a buffer cache, or you have said that the buffer cache mainly consists of two parts. One is the header part and other one is the data part. Okay, so the data portion of the buffer cache must be as large as the disk block size. So a block from the disk will be stored in the buffer cache. So whenever any process requests for the data from a particular disk block, firstly what it has to do is it has to check in the buffer cache whether the data is available in the buffer cache or not. So if the data is not available in the buffer cache, then only it has to be brought from the disk and put into one of the buffer caches. Okay. And we have also said that the format of the header of buffers is something like this. The initial fields in the header that contain the device number and block number, and these two fields identify a particular block on a disk. Then the next field will be the status field, and there are a number of pointer fields. First pointer points to the data area of that buffer. Okay. Then I have two pointers. One pointer points to the next buffer on a hash queue. Then you have a pointer to previous buffer on a hash queue. You have a pointer to next buffer on the free list. You also have a buffer to the pointer to the previous buffer on the free list. Then we are saying the status field of this header contains a number of informations. For example, whether the buffer is currently locked or not. So we have said that whenever a process makes use of the buffer, either for copying the data from the buffer to the user area in the main memory, or whenever the kernel wants the buffer, uses the buffer for reading in a data block from the secondary storage into the buffer, or writing a data block from the buffer to the secondary storage, in all those cases the buffer which is under use has to be locked, so that while the operation is going on, the same buffer should not get access, should not be accessed by any other process. Then the other information that can be contained in the status field is the whether the data is valid or the data is invalid. So while processing, some process may find that the data which is contained in that buffer is an invalid data, it is not a valid data. So whether the data is valid or the data is invalid, that is also contained in the status field. Then other information that you have to put is the delayed write. We'll come to this delayed write later, but it simply says that if in case the buffer has to be overwritten by a new block data, in that case the content of the buffer has to be stored back onto the disk. Then here the buffer may be in use by the kernel for reading in a data block or writing a data block onto the secondary storage. Then I can also have an information that whether any process is currently waiting for the buffer to become free or not. That is, so some process is using the buffer, and while this buffer is in use, the buffer was locked. Okay. So while the buffer is locked, during that time, maybe some other process puts a request for the same data block, and the data block is available in the buffer, but the buffer is locked. Buffer is locked. So in the status field, we maintain some information that whether there is any other process which is waiting for this buffer to become free or not. So in case there is some other process, then when the buffer becomes unlocked or the buffer becomes free, in that case, this process has to be informed that the buffer has become free. Now the process can continue. So these are the different informations that you have to put in the status field. Now the buffer is used for putting the data blocks in the least recently used manner, because I have finite number of buffers in the system, and those finite number of buffers are to be used by the kernel for storage of different data blocks. So it is quite possible that when a new data block has to be read in and put into the buffer, we find that none of the buffers are empty. The buffers may be free. Free and empty is different. Empty means the buffer does not contain any data. Free means the buffer may contain data, but it is not being used by any process at a particular instant of time. Okay. So while reading in a new data into some buffer, we find that none of the buffers are empty. So in that case, as we have done in case of say page replacement policy, that some page which is already there in the frame has to be replaced by a new page from the secondary storage, new page of another process. Similarly, in this case, whenever I want to bring in a new data block and I find that none of the buffers are empty, in that case I have to select one of the buffers which is to be overwritten by this new data block. And for that, again the replacement technique that will be used is the least recently used technique. Now this recently used technique can be implemented again with the help of linked list. We have said because there are a number of pointers in the buffer headers, so it is quite obvious that the buffers are maintained in the form of a linked list. And in this case, the linked list will be a doubly connected linked list because we have two pointers for every queue, one pointing to the next buffer in the queue and other pointing to the previous buffer in the queue. So we have a doubly linked list, and the buffers are maintained in that linked list. So whenever a buffer has to be taken for overwriting the data block by a new data block, then how this is done? We have discussed in our previous course that always it is better to have some header node. Whenever we have a linked list, we should also have a header node for the linked list. This header node will have a pointer in the forward direction that points to one buffer. Okay. For this buffer, the pointer in the forward direction will point to next buffer in the queue. Okay. For this, the pointer in the backward direction will point to the header node. For this buffer, the pointer in the backward direction will point to the previous buffer. So this is the pointer to next buffer in the queue, and this is the pointer to the previous buffer in the queue. Okay. So this way I can put a number of buffers in this doubly connected linked list. Okay. And this will continue, and finally this will form a circular linked list. Okay. So similarly, these backward pointers, they also form a circular linked list. Okay. Now let us assume that all these buffers, this is a free list. That means this header is the header of a free list, and all the buffers which are there in this doubly connected linked list, they are all free. That means they are not being currently used by any process. Okay. And let us assume that the data blocks which are contained in these buffers, they have the block numbers say 5, 2, 15, 32 like this. And if we assume that these are the only blocks, these are the only buffers which are present in this free list. Now suppose a process puts a request for a block number say 10. Okay. And you find, and suppose the block number 10 does not exist in any of the buffers. So firstly, we have to search for block number 10. If we find that the block number 10 exists in one of the buffers, then I don't have to read in a new disk block because the data is already available in the buffer. In case block number 10 does not exist in any of the buffers, then block number 10 has to be read in, and it has to be put in one of the buffers which are currently free, may not be empty. Okay. So if we assume that this is the situation we have, we don't have any buffer which is empty, but we have 3 buffers which are free, and these 3 buffers contains data blocks from block number 2, block number 15, and block number 32. And the request has come for block number 10. Okay. So in that case, what we do is we can take out, the block which is to be a buffer which is to be overwritten, that you always take as the first block or first buffer in the header list in this tree list. So the block which is pointed to by the header node, we take out this block This is the least recently used. I mean, why it should be least recently used, I'll come to that. So what I do is I always take the buffer from the head of the list, head of the queue. Okay, overwrite this with the data from block number 10. Okay, so while the writing continues, this buffer will be locked. When the writing is over, writing is complete, then the buffer will be free. And when you make this buffer free, then I have to place this buffer, the same buffer, now containing the data from block number 10 to this free list. Now, when I return it to the free list, now find that this buffer has just been written by data from block number 10. That means this is the one which is most recently used buffer. Okay. So when I return it to the free list, what I do is, so again, this is the header node. Now, block number 15 will come here, block number 32 will come here. After that, we place the buffer containing data block number 10. So I maintain the free list like this. Okay. So fine. So these are all free lists. So find that if I maintain this policy that whenever I have to take a buffer for writing in a new data block, in that case I will always take the buffer from the head of the free list. Okay. And whenever I want to return a buffer to the free list, I will always return the buffer at the tail of the free list. Now head and tail is with respect to the forward pointers. Okay. So whenever a buffer is free, that means the buffer which has just been used and it becomes free, that means that is the buffer which is most recently used. A most recently used buffer I will always put at the tail of the free list. And whenever I take a buffer for overwriting with a new data block, I always take the buffer from the head of the free list. Okay. So if I maintain this policy, you find that next time, if this is the buffer which is to be overwritten, or this is the buffer which is used, it may not be overwritten, but it is used. The moment it is used, it becomes most recently used. And when it is used, I will take it out of the free list. When work on this buffer is complete, I will return it to the free list, but maybe this time it contains the same data block 15. But when I will return it at the tail of the free list. That means the most recently buffer always remains at the tail of the free list. A least recently buffer always remains at the head of the free list. Okay. So whenever a buffer is to be overwritten, you always overwrite that buffer which is least recently used. The logic remains the same, assuming that a buffer which is most recently used will again be used in near future. A buffer which is least recently used will not be used in near future. Following the same logic, you maintain this LRU technique even for buffer replacement. Okay. So now find that if I maintain all these buffers in a single linked list, a single doubly connected linked list, I may have thousands of buffers in the system. Now suppose some process wants to access a block, a data block, say 12. Block number 12 is to be accessed by some process. So what we said is, firstly the process has to check whether this block number 12 is present in the buffer cache or not, assuming block number 12 is not there in the main memory, not in the user space. So first we have to check whether block number 12 is present in the buffer cache or not. If it is not in the buffer cache, then only we have to read it from the disk, block number 12 from the disk, put it into one of the buffer caches. So to see whether this block number 12 is present in the buffer cache or not, in the worst case, if block number 12 does not exist in the buffer cache and I have thousands of buffer caches, then I have to check all the 1000 buffer caches before I declare that block number 12 does not exist. That means the search time to find out whether a particular block is present in the buffer cache or not is quite high if I maintain a single list. So instead of maintaining a single list, you maintain a number of lists, and that is what are called hash queues. Okay. So in this case, what you do is, suppose I decide that in the system I'll have 4 hash queues. Okay. So I'll number the hash queues like this. So this is hash queue 0, hash queue 1, hash queue 2, and hash queue 3. Okay. Now I'll put those buffers in the hash queue which contains a block number, say n. Okay. And what I'll do is, I'll take the mod operation of n with 4. So I'll perform n mod 4, as I have decided that I'll have 4 hash queues in the system. N is the block number, the block which is contained in a particular buffer. So I'll decide that which buffer is to be put in which of these hash queues. Say buffer containing block number n, if I find that n mod 4 is 0, in that case corresponding buffer will be put in hash queue 0. If n mod 4 is 1, that buffer containing block number n will be in hash queue 1. Okay. Similarly, suppose some buffer contains block number 6. You find that 6 mod 4 is equal to 2. So the buffer containing block number 6 will be present in hash queue 2. So this way it will continue. Okay. So if I have a number of buffers, let me assume that we have a situation like this. In each of these hash queues, I have a number of buffers. So for in each of these hash queues, I have say 3 buffers. Now I find that if I have a buffer containing block number say 28, so if I perform 28 mod n mod 4, that is 0. Okay. So this buffer containing block number 28 will be present in hash queue 0. Similarly, buffer containing block number 4 will also be present in hash queue 0. A buffer containing say block number 64 will also be present in hash queue 0. Right? Similarly, a buffer containing say block number 17 will be present in hash queue 1. A buffer containing say block number 5 will also be present in hash queue 1. A buffer containing say block number 97 will also be present in hash queue 1. So this way I can put different block numbers like this. So because they are bidirectional queues, so let me put bidirectional arrows like this. Something like this. There may be other buffers also in the same hash queues. Okay. And we have also said, and that is also clear from this structure of the header, that every header has got 2 kinds of pointers. We have a set of pointers, forward pointer and reverse pointer, pointing to the next buffer or the previous buffer in the hash queue. We have another set of buffers, a forward buffer and a reverse buffer, and the a forward pointer and a reverse pointer pointing to next and previous buffer in the free list. So it suggests that it is possible that the same buffer may exist in a particular hash queue and in the free list simultaneously. Okay. So the free list that we have drawn in this diagram, this free list is nothing but a subset of the nodes which are already there in different hash queues. Okay. So I can have a situation something like this. If I draw the free list superimposed with this, so for example, suppose this is the free list header. Okay. Then it may so happen that the first buffer in the free list, or which is the head of the free list, will be say the buffer containing block number 3. Okay. So if I follow the forward pointer, this is the first buffer which will be there in the free list. The next buffer in the free list may be say a buffer containing block number 5. Next buffer in the free list may be the buffer containing block number 4. The next buffer in the free list may be the buffer containing block number 28. Okay. The next buffer may be say 97. Next one may be say 99. And this may be the tail of the free list. Okay. So I can have a situation like this. So I have so many buffers distributed in different hash queues, and some of them are free. So the buffers which are free, they also exist in the free list, and buffers which are not free, they exist only in the hash queue, they don't exist in the free list. Okay, how do you manipulate that? Simply by manipulating the pointers. So if I want to take out this buffer containing block number 3 out of the free list, what I have to do is I have to put this pointer to block number 5. Okay, and similarly, the forward pointer from the header node of hash queue 3 has to point to this block number 35. Backward pointer has to of this block number 35 has to point to header queue 3, and the pointers of this block number 3 has to be set null. Simply that is what we have to do to take out this from the free list, or if I want to take out that from this hash queue also. So simplify by manipulating the pointers, I can place this buffer in any of the hash queues, I can put it into free list, or I can even take it out of the free list. Okay. So what will be the initial situation? Suppose when just after booting the system, I don't have anything in the buffer cache. So if there are say 100 buffer caches in the system, then what will happen? All the buffers will be part of the free list. All the buffers will be contained in the free list, but all the hash queues will be empty, because there is no data block in any of the buffer. This is just after initialization. Then subsequently different processes will put requests for different blocks. When the blocks are to be brought in into the buffer cache, then from the free list you take out blocks one after another, write that buffer with the block that is requested, and after putting the block, then only you decide that in which of the hash queues that buffer will be placed, because it depends upon the block number that is contained in the buffer. Okay. So now the advantage that you get by putting this hash queue is that whenever a process puts a request for a particular block, then immediately you perform this hash function. By performing this hash function, you know that in which of the hash queues that block will exist. Okay. So in this case, now we have to search only that hash queue. I don't have to search buffers in other hash queues. Suppose a process puts a request for say block number 9. What I do is 9 mod 4, which is equal to 1. So that means the buffer containing block number 9 will exist only in hash queue 1. It will not exist in any other hash queues. So now I have to search only the hash queue 1. If I get any buffer containing block number 9, then I know that the block exists in the buffer cache. If there is no buffer in hash queue 1 containing block number 9, then I know that the block does not exist in the buffer cache. And how do I check whether the block number 9 exists in this buffer or not? Again by the header, because in the header I have two fields identifying the device number and block number from where the data is contained in that buffer. Okay. So the search time to find out a particular block is reduced to a great extent when I distribute the buffers into a number of hash queues like this. And the hash queue and the free list, they are maintained with the help of same set of buffers. I don't maintain a separate hash queue, separate free list queue. It is by manipulating the pointers in the same buffers. Okay. So what is the algorithm that is to be followed when a process puts a request for a particular block? Okay. So if a process puts a request for say block number 9, firstly we have to check that whether block number 9 is present in the buffer cache. So there may be two situations, either block number 9 may be present in the buffer cache or it may not be present in the buffer cache. Okay. If it is present in the buffer cache, then I can have one of the two situations, that the buffer may be currently locked, that is, it is being used by some other process. So the process who has requested for say block number 9, it finds that block number 9 is present in the buffer cache, but that cannot be immediately used because currently it is locked. So the process has to wait until and unless the buffer is made free by the process who is already using it. And the second option is, it finds that the data is present in the buffer cache and it is free, so it can immediately acquire it. Before acquiring, it has to lock that buffer. The other case can be that the process puts a request for block number 9, it goes to hash queue 1 and finds that block number 9 is not present in hash queue 1. That means the block number 9 does not exist in the buffer cache. So if it does not exist in the buffer cache, then what we have to do? We have to get a node from the free list. We have to get a buffer from the free list and override that buffer with the data from block number 9. Okay. Then again, various situations can arise. Say free list is not free list is empty. That means there is no buffer which is currently free. So again, the process has to wait until and unless some buffer becomes free, which can be overwritten with this new data. I can have another situation that I get a node on the free list, a buffer on the free list, but the buffer is marked delayed write. Okay. Now what is delayed write? While the buffer was, while the data was in the buffer, maybe the buffer was modified by some process. So when the buffer is modified by some process, that modification is not immediately reflected onto the hard disk. The modified data resides in the buffer, but modified data is not there in the hard disk. Okay, it will be put to hard disk only when you close the file. See, whenever you want to process some file, what you do is, first you open the file, then you close the file. Only when you close the file, the process will write the data onto the disk. But before that, the modified version remains only in the buffer, it does not go to the hard disk. But following our LRU technique, if we find that a file which has been modified but not closed, so the modified data is in the hard disk. But that buffer, not in the hard disk, it is in the buffer. But that buffer has to be overwritten by new data. So before overwriting, what we have to do is we have to save this modified data onto the hard disk. So in such cases, what is done is, whenever some modification is done, you simply mark that buffer as delayed write. So that in case it is necessary to overwrite that buffer with a new data block, the delayed write buffers will be saved onto the hard disk before being overwritten. Okay, so that is the purpose of the status delayed write. So I can have a situation like that also, that I get a buffer on the free list and the buffer is marked delayed write. So I have to initiate writing the buffer content onto the hard disk, and that will obviously take some time. So instead of waiting for that writing operation to complete, why don't we try for some other buffer which may be free? Okay, so that is not harmful, but it will make the process faster. So I can have various such situations, and let us see in the form of algorithm how these different situations are taken care of. So the algorithm that is used for getting a block, a disk block, is Let us term is as say gate block algorithm. Okay. And what will be input to this gate block algorithm? That is a file system block number. A process has put a request for a to access a particular block number. So the input will be the file system block number, and output will be a locked buffer. Okay, the locked buffer which will be given to the process for operation. So you can put the algorithm like this, that while buffer not found, the algorithm will continue like this. Whenever a process puts a request for a buffer, that is a system call, and now the kernel or the operating system has to get the buffer, get the block for that process requesting for it. Okay. Then the kernel will work like this, that while buffer is not found, it will continue. That means it has to get, the kernel has to get some buffer for the process who has requested for it. Maybe the buffer containing the requested block, or a free buffer where the requested block can be put in. Okay, so the kernel has to return a buffer to the process who has requested for a particular block. So as I said that there can be two different situations, that the block is present in the hash queue or the block is not present in the hash queue. If the block is present in the hash queue, that means it is it means that whichever data is requested, that is already present in the buffer cache. Okay. Otherwise, the data is not present in the buffer cache. So if the block is present in the hash queue, but so there should be one more condition, that the block is present in the hash queue and at the same time the block is locked, the buffer is locked. Okay, I'll put it here. If buffer locked, okay. So I can have a situation that the block is present in the hash queue, but the buffer is marked locked. That means the data is present, but it is being used by some other process. So in that case, the process who has requested for it, that has to go to sleep mode, and it has to sleep until and unless this buffer becomes free, because there is I don't have to get a new buffer for reading in the block again and put into one of the buffers, because in that case there will be duplication of data. So to avoid that, the process who has requested for this block, that goes to sleep mode, and it will be in sleep mode until and unless this buffer becomes free. Okay. Otherwise, if the buffer is not locked, then you simply mark the buffer as busy, because this buffer has to be returned to the process who has requested for it. You mark the buffer busy, then remove the buffer from the free list, because at least as long as the process requesting for it will use the buffer, it will not remain free. So you have to remove it from the free list and return this buffer to the requesting process. Okay. Now in case the block is not in the hash queue, then as I said that the data is not present in the buffer cache. That means I have to get a buffer where this data block has to be written. Then I can have a situation that there is no buffer on the free list, that is free list is empty. So if the free list is empty, then the process goes to sleep mode on event that any buffer becomes free. Now find the difference. In this case, the process had gone to sleep mode and it will sleep until and unless this particular buffer becomes free, because now the buffer contains the requested data. In this case, there is no buffer which contains the requested data. So now the process has to go to sleep mode, and it will be in sleep mode until and unless any of the buffer becomes free, because any buffer becoming free is sufficient, because that buffer will be overwritten by the new block. Okay. So now the process goes to sleep mode on event that any buffer becomes free. In case there is a free buffer on the free list, in that case what you have to do is simply remove the buffer from the free list. Then after removing this, we may find that the buffer is marked delayed write. Okay. So the buffer is currently free, but it is marked as delayed write. So if it is marked as delayed write, then we have to write the data into the buffer onto disk, then only the buffer can be used. So what is initiated is an asynchronous write buffer to disk. Now there is difference between asynchronous write and synchronous write. In case of synchronous write, the process has to wait until and unless the write operation is complete. Okay. But in this case, the process need not wait. The process initiates asynchronous write to disk, and just after initiating the write, it can start searching for another buffer. If there is any other buffer which can be immediately used, it will grab that without waiting for this write operation to be complete. So if the buffer is marked delayed write, it initiates asynchronous write buffer to disk and then continue. Continue means goes back to the while loop, where it tries to search for another buffer. So it is not waiting for this write to be completed, and then only, it is not that only this buffer will be given to this process. It simply initiates writing operation, and after that tries to search for another buffer which can be allocated to this process. Once the buffer is available, then the buffer will be removed from the old hash queue, because the buffer was already containing some data. That means the buffer was present in one of the hash queues. Okay, and maybe a new block that will be put into the buffer will put the buffer in some other hash queue, not the old hash queue. So you have to remove the buffer from the old hash queue, put the buffer in the new hash queue, and after that this buffer will be given to the process, okay, when a new block will be written into the buffer. Okay, so this is how, whenever a process puts a request for a particular block, the block allocation will be done. Okay. Similarly, there has to be a free block algorithm, because whenever a process releases a particular block, it releases a particular buffer, then the buffer has to be put in the free list. Then, as we said, that always the buffer is put at the tail of the free list, but it is not always so. There is a situation when the buffer can be put at the head of the free list. That is, while processing, if the process finds that some block contains invalid data, then it is not at all wise to put that buffer at the tail of the free list, because in that case there will be a buffer in the free list throughout its lifespan which contains an invalid data. So if there is an invalid data into any of the buffers, it is better that you override that invalid data by valid data as early as possible. Okay. So in such situation, if there is any buffer detected containing an invalid data, then instead of returning the buffer to the tail of the free list, you return it to the head of the free list, so that the next buffer to be overwritten is that buffer which contains invalid data, and hopefully this time it will be containing a valid data. Okay, so that way, whenever you return a buffer, the buffer may be returned either at the tail of the free list or at the head of the free list, but buffer can never be returned in the middle of the free list, either at the tail or at the head. Normally at the tail, but only in special case when the buffer is detected to contain an invalid data, it may be put at the head of the free list. But whenever you take a buffer for overwriting, you always take the buffer from the head of the free list. That always ensures that either you are taking a buffer which contains an invalid data, or you are taking a buffer which is the least recently buffer. Okay. So next day we'll continue with this.